to a question sort of just reviewing and looking forward a little bit from last week. So here's our first example today for the learning catalytics. And so here's, again, this is an old test question. And so you got 4 charges, 1, 2, 3, 4. This is supposed to be a square, A, B, C, D, 3 positive, 1 negative. I want to know is what arrow here is most close to the direction of the force on charge A. So talk with your neighbors and we'll see what we come up with. Okay, so I think we're getting there. So maybe give ourselves 20 seconds. And again, if you're sort of working on this and not quite there yet, just go ahead and guess and we can talk about it. But at least you got a chance to kind of think about it or something. Okay, so I'm going to go ahead and stop. Actually, so here's the results. Did you guys see that when I do that? Oh, good. And so I think I agree with the majority. So let's talk about this. This is, again, is a one that deals with vectors. So how do we do this? Well, we use the idea of superposition, right? So we just go through and figure out the different forces that are acting here. And so in this case, let's do it for this one here. And so between A and C, the force should be repulsive. So I'll draw the force kind of like that. So that's the force acting from C. Between A and B, it should be attractive, something kind of like that. And something important that I'll draw here is that these two forces should be the same length of vector. So I tried to do that. It's not perfect. But because it's the same size charge and it's the same distance between them, these here should be the same. All right, and so now we've done these two, and we want to do this one over here. Okay, so this one's going to be repulsive. It's going to point this way. And what's really important here is that we draw this vector, okay, a little bit shorter. So this is the force from D. All right, and why is that? Well, because the distance between here is going to be this hypotenuse, which is longer than the distance between A and C and the distance between A and B. And that's sort of key. Okay, and so now we see, well, we've got sort of 3 vectors and they're all doing different things. But what do we do with this? Well, we end up adding up all the components. And so if I look at this little tiny guy here, again, it's a smaller vector. And so if I break this into components, that way and that way, what's going to happen is when I add everything up, this force of FB is going to be much bigger than this one here. And so the overall in the x direction force will point to the right. And the thing is the 2 up forces just point up. And so those will go up. And so overall the vector will point in a direction kind of like this here. Okay? And so this is superposition, but it's sort of a superposition all in our head. Okay? And so and the key point is that you knew this vector had to be shorter than these two because that distance was longer. Okay, so without that sort of piece, this is really tricky to do. Questions on this one? So today we're going to deal more with the electric field, but these sort of concepts of dealing with vectors will be the same. Okay, and the majority sort of agreed, I think, so that's good. All right, so just introduction. So I'm sure you've read about this, the electric field. So we like to think about our charges as applying a field in the space around them, okay? And so we like to say that every charged object makes an electric field in the space around it. And this field helps us describe the force that the field will exert on other charged objects. Okay, and so we think about this field as giving rise to the electric force a particle will feel. So it's a kind of a nice way to think about it and for us to visualize it. All right, and so the way it is, sort of, you think about it, is the charge creates a field, and this field is what applies a force on another charge. All right, and here's some questions from you guys. Again, really great questions, thanks. In fact, there's so many questions I can't answer them all. I tried to put as many as I could, so please, if you don't get it answered, put it up on Piazza or something. But great questions. What exactly is the electric field, since it seems to be different than the charge? What is it composed of? Well, that's a great question, sort of a difficult one, but the idea is that the charge creates this field in the region around it. Okay, so it's different from the charge. It's sort of the effect that the charge has in the region around it. Do electric fields only affect points in space, or do they affect charged particles? Well, the way we think about it is we think about the field as existing in points in space, and then what happens is if we happen to put a charge somewhere, it affects the charge, okay? So it doesn't really affect points in space, it sort of exists in points of space, all right? And the only thing it really affects is other charged particles, but it's a way for us to sort of think about this electric force in a different way that we'll sort of see. It'll be helpful to us in lots of cases. And I still don't understand the concept of electric field and how it ties into charge. Like, how exactly do Q, F, and E differ? Well, they're actually very related, and so we'll get into that in a second. Try to answer that question in a slide or two. And so here's pictures that you'll see, electric field lines. So I show you some of these. The book sort of shows you some of these. And so here, someone asked in the video, you showed a picture of a negative charge surrounded by arrows. That's this one here. I don't get what the arrows with different size indicate. Does it indicate the magnitude of F? Well, no, that's not right. It indicates the magnitude of the electric field. Okay, so that's what we're indicating with these vectors here. And so there's different ways to write this, but here, one way to write this is we draw little dots, and the arrow points in the direction the electric field points in, and the length of it tells you how big it is. And hopefully that kind of makes sense. The electric field here is bigger because it's closer to the positive charge than this one is. So here it's a little bit weaker. And the same thing over here, okay, the arrow here at this point is larger than this one because it's a closer point. And the convention that we choose is that the electric field points the direction that a positive charge would feel a force. And so if I was a positive charge here, I'd feel a force away from the positive. If I was a positive charge here, I'd feel a force towards the negative. All right, that's what these pictures are trying to represent. And so here's the relationship between these letters. Okay, so basically the force is the electric field times the charge you put there. Okay, so if you have some electric field in the space around you and you put a charge in there, to find the force, it's just the charge times the electric field. And so that's our basic definition. Okay, electric field points, again, by this definition, in the same direction as a force of positive charge would feel at that position. Okay, and so electric field is just the force divided by the charge that's feeling the force. The units are newtons per coulomb, so force is newtons, charge is coulomb. Here's a good question we had last night. Also, what is a coulomb? Like, is it randomly defined as this many electrons? So it's not randomly defined, but when they first came up with these numbers, when they first did these initial experiments, they were dealing with really big things like large metal balls. They didn't really understand that charge came from electrons, and so if you have a big metal ball, okay, it can accumulate an awful lot of electrons. And so when they defined the coulomb, it was defined this way and not with a knowledge of the electron. So unfortunately, when we learned about the electron, it's a super tiny number as far as coulombs go, but as far as things you might deal with every day, it'll be a much larger number. But it's just, you know, somebody who was doing experiments just sort of came up with what they thought was a good way to describe it. Okay. All right, so let's do another question here. And so this is, you know, again, an old test question. And so here's, now this happens a lot. Okay, this is a question that, it's a 132 question, but it uses some knowledge from 131. Okay, so we'll talk about this as we go along. And so here we have a small sphere is suspended from a string in a uniform electric field. So it's an electric field that's constant. And several different cases of sphere and mass ratios are put up here. In which case is the angle at which the sphere hangs the smallest. Okay, so which one of these cases will have the smallest angle? Here's the charge of the sphere, and here's the mass of the sphere. So talk about this with your neighbors, and we'll talk about this in a second or so. And again, we're trying to find the case with the angle which is the smallest angle. Okay, so let's go ahead and call time in about 10 seconds or so, and we'll talk about this one. So here we have the results, and I think I agree with the majority, which is good. All right. Okay, and so let's think about this one. So again, I think everybody, or a lot of people got this one, so it was B. That was the most popular choice. Now, a lot of different ways to think about this. How I would think about this is just, again, we got to think about this like a 131 style problem. What are the forces acting? Well, the forces acting would be downwards, there's the mg, and this way there's the new force, the 132 force, force of electric field, and then there's this tension force like this. Okay? And now if I was to draw a little picture of this, of the tension, so the tension is going to look kind of like this here. So tension is going to have my tension, the x direction of the tension, and the y direction of the tension. And here's the angle, the way we defined it. And that angle is going to go like tx over ty. Okay, you can think about it kind of like a tangent. So tangent is opposite over adjacent. Okay, so tx over ty will give you the tangent of that angle, which is going to basically give you the sort of the bigness of that angle. Okay, the bigger tx is relative to ty will give you a bigger angle. And then from this picture here, you can see that the tension in the x direction will equal the electric force, and the tension in the up and down direction, y direction, should equal the mg. Okay, so we can sort of then take that and equal it something kind of like this here. So the electric force is Q times E. We just learned that one. That's brand new. And the gravity force is mg. And so the key thing here is this ratio Q over m. All right, because the two letters in there, the electric field and the G are constant. The electric field is constant, the G is constant for us. And so this here, the bigger Q divided by M is, the bigger that angle will be, and vice versa, the smaller it will be. And if you go through here and divide Q divided by M, like 4 divided by 2 gives us a ratio of 2. 4 divided by 3 gives us a ratio of 1.33. 6 divided by 3 gives a ratio of 3. And you can just do the rest of them. 2.67 is that ratio, and 2.25 is that ratio. So the ratio of that's the smallest would be that B, which of course is the one that we were looking for there. Okay, so this will happen a lot in the sense that it'll be sort of some proportion of the problem is 131, some proportion is 132. Okay, so you got to do these examples and sort of, you know, kind of just sort of jog your memory sometimes with this stuff. Questions? Okay. And here's just, this is one of your questions from Practical this week, which again is another one of these 131 sort of style questions. Okay, so you're given an electric field, you're given the mass, and you're trying to find the position of the particle at some time. And so you're actually going to end up using things from 131 for that, to sort of try to tie in the practicals. It's another example of an old test question. Just keep you kind of, show you in mind. Okay, so PCQ number 1, people did really well on that, so I won't spend too much time on this one. Again, it was asking you a step-by-step process of how you would figure out, and so here's one answer from somebody. A tiny positive chest charge will be placed at the point in space, and the force will be measured from the force measurement and the charge. The electric field can be calculated this way here. The direction of the field will be the same as the direction of the force since Q is positive. That's exactly perfect. Some people wrote them out steps like this. That's totally fine too. Place a positive charged object at the point. Calculate the acceleration. This person get pretty specific. That's great. Of the object moving using a motion sensor. Find the force of the object experienced. Find the charge. And then use that equation to find the electric field. Those are totally acceptable. So I think people got that point here. So basically, and again, this is the idea of a test charge. People are still asking questions about test charge. It's basically a charge that we put in to sort of test and learn about different circumstances. It's usually really tiny. It can be positive or negative depending on what we want to do, but usually positive is the way you want to go, because in most cases that's what you're trying to do. Like in this case it was much easier. Like if you put a negative test charge in, you'd have to reverse the direction, which isn't that bad, but why give yourself another step, right? Okay, and so that was good. So then we move on to the electric field due to a point charge. And here's our equation here. It's very similar, and we're going to use it in a very similar way to our last equation from last week. And so this is how you figure out the magnitude, and then with direction, here's how you find the direction. Okay, so for a positive charge, the field points away from it. For a negative charge, the field points towards it. And again, this convention is set up so that if you put a positive charge there, the convention is which way would the force be, and that's how you draw this out. Okay, and so for instance, if I put a positive charge there, it would feel a force of repulsion from that guy. It would feel a force of attraction from that guy. A lot of questions, a lot about this sort of idea. Is the direction of the field vectors just a convention that all people agree on to make communication easier? I would say yes. It also comes from, you know, our equation that we wrote was this here. So force equals Q times E. So when I wrote that equation, when whoever wrote that the first time, they're saying that the direction of the E field should be the same as the direction of the force if the charge is positive. So if this is positive, they should have the same. If this is negative, they should be opposite. So it comes from here, right? But the person who invented this could have made a negative there if they wanted to. Okay, it just would have made things a little bit different. It's just a convention, right? So I think anytime you add a negative, that's kind of a bad thing. But really it is just a way to make communication easier. But it does come from this equation here when you're looking at it there. Okay, so again, good questions. And just to kind of show you how these things connect, got a lot of questions about this here. So these things, this is our electric field. So say I found the electric field from a charge. I'll call it charge number 1. Well, I'd say KQ1 over R squared. Okay, and then say that I put charge Q2 at some distance R, and I wanted to find the force on it. Well, I'd do Q2 times that electric field 1. and I'd end up with, you know, KQ1 over R squared times Q2. So I end up with the same equation. Okay, so these equations, the one we had last time, this new one and this other new one, are all interrelated. Okay, and the idea with the electric field is just to make this a little bit easier in calculating, a little bit. We can actually use the electric field to hopefully try to understand some things too. Okay, so this is from last night. A lot of questions on this one. That's good. Let's go ahead and ask this question. This is really similar to the one we had last time. Okay, and so we're set up here with one charge which has like 4 x's, or 4 positives, and one charge that has 1. And I want to know is, where in this is it possible to have a 0 electric field? So the question they asked you last night was, where can the electric field be 0? Well, here what I want you guys to come up with is, which region is it possible to be 0? That's usually the first step. Okay, find the region where it's possible to be 0. Then that makes your life a lot easier. Okay, so think about this with your neighbors and let us know what you come up with. Is this the catalytics? Can I see what you see? I've never done it as a student. So did you answer already?
Yeah, I did.
And then can you see the results?
At the end.
At the end?
Mm-hmm.
Oh, okay, thanks. Okay, so I think the good news is we did really well on this one, so I'm going to call time now. So give yourself 10 seconds to put an answer in. And if you didn't quite get it, we'll explain it. Again, hopefully being able to talk about it for a little bit helps. So we'll stop, and that should, I think, we're showing you the results now. And I agree with the majority, which again, it's really similar to what we did last time, so region B. So if you look at this here, the way I would think about it is, again, you put a little test position over here. Now when we're finding the electric field, we don't put a charge there, we just put a little position there. And so if I put a little position there, the electric field points away from positive charges. Okay, so for instance, if I call this charge 1 and charge 2, that's a work. And so basically the force from the electric field from charge 1 will point that way, the electric field from charge 2 will point that way. So it's possible, since they're in opposite directions, they'll cancel out. If you look at a point in one of the other regions, so let's put a point over here, all right, the electric field from charge 1, whoops, electric field from 1 and the electric field from 2 point away, they're in the same direction, they can't cancel out. And the same thing over here. Okay, so region B is the only place that can happen. So that's the first thing you want to do with a question like this. Now the second thing is you want to take this and then kind of think about, okay, so it's in the middle region, and kind of go through and think about what it's going to be. And in this case, it's actually, you can say, well, the magnitude of the E from the 4Q. So I'm going to say that it's a size of 4Q, since it's got 4 pluses. So 4Q over, I'll call it R squared, and so I get 4KQ over R squared. And over here, E to the Q is going to be KQ over R squared. And so I'll separate these, but I'll call them like R1 and R2 because they're different distances. And so in this one here, you can actually kind of reason it out. You can say, well, let's try this point right here, okay, 0.6. Let's just see what happens. Well, if I try 0.6, okay, the distance for the 4Q is 2. And so I get 4kq over 2 squared, which is 4. And so I get kq over 1 when I figure that out. And over here, if I do kq over this one, well, the distance now from that to there is 1. And so it's kq over 1 squared, which is 1. And so these two guys are equal. Okay, so in that case, it actually worked out really easily, okay, that you could get that sort of right away. And we'll show you how to do one that doesn't work out that nicely in a second. All right. Okay, so let's take a little break. So I know here's just a little list of things that are more difficult than physics. Because I know right now maybe you're thinking there's not that many things that are like that. But you guys actually do a lot of things. So here's the first one, commuting in from far away, especially in January, right? That's really, I think, more difficult than physics. Catching a streetcar at 1 a.m., everyone had to do that before. That can be tricky. Conversing with your hairstylist. I have a lot of trouble with this myself. Crossing the street between Hart House and Queens Park. You know that place? Oh man, that's where I'm going to be ended, I think. Okay, there you go. Yeah. That's really more difficult than physics. Just joking. Buying groceries at the Metro in Bloor-Spadina. You guys know this place? It's like super tiny. Like when I walk through the aisles, I knock stuff off the aisles with my shoulders. Getting good service at a Kensington Market coffee shop. Especially when you're an old guy like me, that's really tough. Figuring out which way to head after you exit a subway station for the first time. You ever do that? And then you check your phone to kind of see yourself on the Google map, and it's even harder to figure out where you really was before. Differentiating a black sock from a navy sock. I'm like really bad at that. And then finally, following the plot of Game of Thrones. I'm so confused. Okay, so again, just to kind of get you ready for your practical this week, I wanted to talk about this idea of polarization. And the way we're going to sort of do it is show you this sort of classic thing, hopefully it works, of using a balloon. So you've probably seen someone do this. So they rub their hair on the balloon, right? And they go over here and they put it somewhere and the balloon hopefully will stick. Whoa, whoa, magic. All right, so what happened there? Well, what happened there is when I rubbed it on my hair, I transferred some charge. And let's just say that what I did is my hair stole electrons from the balloon. So the balloon has some positives. They don't have their buddy electron anymore. Okay, and so the balloon is positively charged. But the question is, well, why does it stick to the wall? The wall's neutral, right? I didn't do anything to the wall. Well, what it is this idea of polarization. When I brought the positive charges close to the screen, the little atoms there got what they call polarized. Okay, and so the atoms, the electron kind of moved closer to the balloon and the proton moved further, and so you get this effect that's called polarization. So last time we saw this with a tin can, right? But it also works with materials like the wall here. But in this case, the electron can't leave the atom, but it can slide over. And so then when you bring the balloon close up, these electrons are closer, and so there's a positive force. Because these are closer, there's an attractive force between this. Now, it only works for a balloon because a balloon's really light. Okay, if I put my head over there and tried to, levitate myself, it wouldn't work. Okay, but it does work in this case because it's a pretty small force because of this polarization effect. Okay, and this is the thing that's going to be the trickiest part of your lab is you're going to charge up these balloons, and the balloons are going to want to stick to everything because of this idea of polarization. So you got to get sort of good at realizing what's polarization and what's not. So let's see, some questions. What do you mean by polarizable object? What properties these kinds of objects have? Basically, everything is polarizable. Okay, everything is going to be like a metal or an insulator, and it just basically means that when you bring charge up to it, the electrons have some ability to kind of move closer, and the protons move further away, is the idea of polarizability. And someone asked, if a charged object can attract an uncharged object, then how to calculate the force between them? That's a great question. question. So someone asked this last time too. Basically, it's really complicated to calculate the force of attraction here, right? All that we know to deal with is point charges, and these things are a bunch of point charges. We don't really know how many, and so it's really tricky. So we won't ask you to do that. We'll more ask you questions that are conceptual in nature. Okay, we'll point out though that in the book we've talked about this idea of fields of point charges and charge distributions. That would be what this is here. Okay, in a case like this, the way you deal with it is you try to find this charge and break it up into little point charges and then use our equations. Okay, and so you try to find little tiny charges, treat them as point charges, and then add them up. Okay, now we'll deal more with this later, but that's just sort of the way you would do it. We won't get that complicated here, but just to kind of let you know you can do that. Okay, so here's some questions from you guys. Again, great questions. In the last example of the pre-class video, instead of using, I did it like 2e cosine 45, could you have used the Pythagorean theorem to find the hypotenuse? You can do these problems any way you want, okay? So I'm going to try to show you the way that I think is the simplest and the most straightforward. If you have a different way that you learned in high school or whatever, as long as you get the right answer, we'll be able to figure it out, and we don't care how you get there. And we'll never ask you a question about some sort of like R hat or something, so it's totally however you want to do it. How can we explain the procedure to find the direction of the electric field? Do we need to explain something like we need in the question 1, or just need to figure that out without the explanation on the test? So I think they're talking about that number 1 from the PCQ, and I think it's definitely fair game that we could ask you a question like that PCQ on a test, okay? And so you want to be able to calculate this, but you also want to be able to explain like you did in that PCQ1, okay? What is electric field in the middle of a point charge, like right on top of it with 0 distance? Okay, this is a pretty deep question. And basically, the short answer is we'll never deal with that, okay? But if you think about it, our equation goes as 1 over r squared. If you put a 0 down there, the thing gets infinite. Okay, basically the problem is we don't know how big a point charge is. Like an electron, we don't know the size of it. So we approximate it as a point charge, but we're basically putting all of the charge at the 0 position, which is like basically saying it's all put in there in a 0-sized box, which is sort of impossible. So basically the equation we have sort of blows up when you get to that point. So we will never deal with that, but the answer is you need to sort of look and figure out what the size of it is, and unfortunately no one knows what the size of it is, so there's not really even an answer right now for that question. Can test charges be positive and negative? Sure. Like I was saying, I mean usually they're positive, but last time I made a negative test charge to show you that the positive and negative answers were the same, so you can definitely use either one, sort of what you want to do. Okay. So now let's go back to this PCQ, and this is the other one you had, which I think is a little bit harder. And again, it's the same sort of idea. So at which points is the electric field 0? Okay, and so I'm going to show you how to go through and do this here. Now, in this one, okay, if you look at the electric fields, okay, over here and over here are the regions where they can possibly cancel out. Okay, because they'll be in different directions. And like we did this last time, okay, the point over here will be where our special point is. Okay, and so that'll be where our special point will be, somewhere in this region over here. So over here, again, if we label these, let's go ahead and label these. This is the 4Q, and this is the negative Q. Okay, if I label these, the negative Q's electric field will be this way, so negative Q, and the 4Q's electric field will be that way. So they're in different directions. Again, for the positive charge, it points away. For the negative, it points towards. And like last time, it's going to be 0 over here because you want it to be 0 at a place where you're closer to the smaller charge. All right, again, it's like two people are talking. This person's really loud. This person's really soft. You want to find a point where you hear them the same. That's going to be over here, closer to the person who's whispering, not over here, closer to the person who's yelling. Okay, so the first step in these is always to figure out what region you're talking about. So that's the region. And then the next step is then to do some math. And so the first thing I'm going to do is call this distance over here x. I'm going to label the distance from the negative charge. Okay, so since I know it's on this side over here, I'm going to call the distance from there to there to be x. Okay, and then what I want to do is I want to do this. I want to find the point where the magnitude of the 4q is equal to the magnitude of the negative q. Okay, and so what do? Well, I plug in my new equations. Okay, and so for this one here, it's k, the charge of that guy is 4q, and the distance here to this point, so we're doing the distance to this point, is 1, 2, 3, since there's 3 spaces here, plus x. So whatever x happens to be, this distance is 3 plus x. And this is sort of the part that I think is maybe most confusing, but for this all the way over to here, right, this distance is 3 plus x. And so what I put down in here then is 3 plus x squared. Now for the negative charge, it's a little bit easier. Okay, so it's k times q, and the distance from the negative charge to the point I'm talking about is just x squared. Okay, now once you have this, the physics is over, and it's all math. Okay, not to say that it's easy, but the physics is over, and now it's all math. Okay, and so you basically want to go through and solve this equation. There's different ways to do it. Okay, the first thing is get rid of the k and the q. That feels really good to get rid of those. So you have an equation here. Now here, I then take this and wrote it out like this here. Okay, so I basically divided the 1 over here, brought the 3 plus x squared over to here. Now one way to do this is to square the top and go through and make this into a quadratic equation. That's totally a great way to do it. A lot of people do it that way. Another way to do it is to take this and take the square root of both sides. Okay, it's a little bit faster, all right, and you come out with something kind of like this then. Okay, so if you take the square root of both sides, you come out with, well, the square root of 4 is 2, and over here this will be the square root of 3 plus x over x. Okay, now the problem is I forgot something that your math teachers probably told you never to forget. Anybody know what I forgot here? Yeah, a plus or minus sign. Okay, now the good news is you only have to do it over here, but you got to do a plus or minus sign. Okay, and so now if I go through and do this, I get plus or minus 2x equals 3 plus x, and then I just go through and solve that equation. And so I'd get plus or minus 2x minus x equals 3. And this will get me to 2 solutions. It'll get me to negative 2x, negative 3x equals 3, which gives me x equals negative 1. That doesn't jive with what I know I want to have happen. And the other answer is x is equal to 3. Okay, so like any quadratic, I get 2 answers, and basically like usual in physics, when you have a quadratic with 2 answers, one of them doesn't make any sense. This one here is telling me the answer is actually over here, which that doesn't make sense to me. I know they can't cancel out here, they have to cancel out over here, and so this has to be the right answer. Okay, and so 3 units from here would be 7, 8, 9, and so 9 would have been the answer for this particular one right here. Okay, now again, you can do this, or you can actually do the long quadratic. You get the same answer either way. It's up to you. There's lots of examples of this on old tests and things. And to be honest, this is actually the kind of problem that if we put on a test, you guys get really good at these ones. So I wouldn't stress too much about it, but it's good to have gone through it. Any questions on this one here? Again, the key is to find where the 0 point is, okay, before you sort of get started on that one. And just to let you know, this is how you would solve the problem from last time too, okay, if we actually wanted you to find it. And so you can think about these problems as being very similar. You know, and you think about it, if you want to find the place where the force is 0, that's also finding the place where the electric field is 0, right? Since we know that our equation, force equals Q times electric field. So these problems are definitely related to each other. Okay, the last thing I wanted to do today is talk about this guy. And the book likes to make this really confusing. Does anybody know what the book calls this? This is a positive charge and a negative charge of equal size sort of hanging out with each other. What does the book call this? Anybody know? A dipole, okay? But literally all that it is a positive and negative hanging out together. So let's talk about this for a little bit. Okay, so the first thing is we have this setup, a positive and a negative, we call a dipole. What's the direction of the force over here at point A? Okay, so you guys think about this and let me know what you come up with. What's the direction of the force for this dipole here? Okay, looks like we're doing really good. Let's give ourselves maybe 15 more seconds on this one here. So the point we're trying to make is that, you know, this dipole stuff, once you guys know how to do point charges, the dipole stuff isn't so bad. And I think this is a good example. So this is, everyone's doing really good on this one. And so I think we're thinking about this one as being a pretty one of the more straightforward ones to do. Okay, so I'll give you 10 more seconds. So again, if you're not sure what the answer is, just go ahead and guess and we'll talk about it. Okay, so we'll stop. And this is real similar to the one, again, I think like 90% of you guys are pretty close, got this answer. And so the idea again is the electric field, and in this case here, is going to point away from the positive charge and towards the negative charge. And so this is one of those deals where the up and down cancels and the pointing that way is going to double up. Okay, and most of us have got that. Now here's the thing that the book does, is it goes a little bit more in depth. And so it wants you to say, okay, it doesn't just want you to find the direction, it actually wants you to find the magnitude. And so let's go through and find the magnitude. So to do that, what's going to be really important is drawing a little triangle like so. And so here's, I'll call this the angle theta. This side is A. We're going to call this thing here the origin. Okay, and so that means the height here is y. So this is typically how we do problems like this. And so one thing I'll do with this little triangle is I'll write the hypotenuse. The hypotenuse is y squared plus a squared. Okay, and so these triangles can be really scary, I think, when you're watching someone do them. So you definitely want to sit down and do this yourself. Once you do it a few times, it's just doing the trig, which you guys seem to be really good at. So a squared, y squared, that's the hypotenuse. Okay, and so now I want to try to develop what I'm going to call the electric field from the positive charge. And so this over here is that electric field. Okay, and so I'll call this the electric field from the positive charge. And so what do we get that? Well, it's going to be KQ, right, over R squared. Well, R squared is going to be the y squared plus a squared. Okay, so we're going to do this just like we would have done this a vector problem last time. So the sort of, we'll call this the electric field from the positive charge, and it's just KQ over R squared, which is y squared plus a squared. And I think I'll go ahead and change this to positive so we can see this. And so what I want, what I'm interested in is the positive in the x direction, right? Because that's the one that's going to double up. So I get y squared plus a squared down here. And so if I draw my little picture, or sort of add to it, right, there's 2 points. There's this point here and there's this point here. I care about the E positive in the x direction. That's the component that I want to find. And so how am I going to do that? Well, the easiest way to do that is to say cosine of the angle theta, right? This angle here will be the same angle as the one down here, and so I want to go through and find that angle theta. Well, what is cosine of theta? Well, I'll do SOHCAHTOA, and so it's A divided by H. Okay, and so from this I get KQ over y squared plus A squared. Now, A over H. If I look at my diagram here, okay, so this is the theta. I want adjacent over hypotenuse. The adjacent will be the A, and the hypotenuse will be this. So it gets pretty ugly, but again, it's just our trigonometry. Okay, so radical y squared plus A squared. Okay, now if I clean this up a little bit, I get that the positive E plus in the x direction is going to look like this. And again, this is just the magnitude of it. It's going to be KQA. Now this is kind of tricky. Y squared plus A squared. Okay, this is another math thing. So here I've got y squared plus A squared to the 1 power, y squared plus A squared to the 1/2 power. And I multiply them together. 1 plus a half is the 3/2 power. So this is the positive, or the x direction for the E positive looks like this. Now we know from that last clicker question, the negative is going to be the exact same thing in the x direction. And so for the last step, I just multiply everything by a 2. Okay, and so the x component for this guy will be 2KQ over A over y squared plus A squared 3/2. Now, since we're typically doing this kind of an x and y axis, which will be the way we'll almost always do it, unless we tell you otherwise, then this would be negative. Okay, we saw that in the clicker question. And so that there would be our answer for this. So the book goes through and develops this equation. Okay, we'll never sort of need you to sort of memorize this equation. However, if you look at old tests, sometimes we'll have you go through and derive this equation. Okay, so you want to be able to go through these steps. And there's another example this week in practical doing that. Okay, so again, there's a lot of steps here. I'll post these notes. You want to go over this yourself and make sure it makes sense to you. Okay, but it's really just kind of doing that first part we just did there. Now, one step before you go here, the last thing in the sort of few minutes we have left here, okay, is now most of the time these problems will have you do one last step. And here the one last step is, okay, so here's the equation we just derived, okay? What does this equation look like when y is much, much bigger than a? Okay, the book does this, and this is also a good way to sort of test yourself. Okay, what does this look like when y is much, much bigger than a? Okay, how does this go? And so think about this here. Does it go like 1 over y, 1 over y squared, 1 over y cubed? What does it go like? So think about this with your neighbors, and we'll talk about it here in a second. And so one of the take-home messages here is this idea of electric dipole. It's just 2 point charges. And so once you know how to deal with point charges, you know how to deal with a dipole. It's just sort of a different, they give it a name basically. They say here, if these 2 charges are here, we're going to call it a dipole. But it can sometimes be a little scary, I think. Okay, so it looks like most people have responded. So again, think about this. Which does this go like? 1 over y, 1 over y squared, 1 over y cubed. Okay, so let's go ahead and talk about this one. So first of all, okay, the answer we get for this, which I think is the majority answer, is this one right here. Okay, so let's talk about this and sort of show you how this works. Okay, so E, the total, if y is much, much bigger than a, then downstairs what I have is y squared to the 3/2 power. Okay, this would be approximate. Y squared to the 3/2 power is going to be y cubed. So 2kqa over y cubed. Okay, and this is important because this is how, in general, okay, the dipole is going to go like y cubed for large distances. And why is this important? Well, it's important because what's happening is because the two charges are sort of canceling out, okay, this thing sort of drops off faster. Y cubed goes to 0 faster than y squared does. Okay, and again, you'll have one in practicals that's similar to this. It looks kind of like this here. All right, so we'll see you guys next time. Thank you.